Imagine we are in the middle of a cell and we are watching the proteins, the people here at work. Now there's many that we immediately recognize, construction workers that put up new buildings, doctors that go to work. But what if there's many more actors, maybe some that we don't see at first sight, that change how the cell works for the better or worse? It is those small and unknown proteins that we are interested in studying.
If the human cell was a town square, the proteins would be the workers. They construct buildings, collect garbage, and repair damage. But when cancer takes over the cell, proteins can start behaving differently and become destructive. But were there other actors involved in making the proteins shift their behavior? That's what Simon Elsesser wants to investigate further.
If we talk about cancer, we could imagine many people stop doing their work. We suddenly put all the energy into building new buildings instead of taking care of, the infrastructure and the environment and the garbage collection. And so we really like to understand what are the culprits of this transformation from a happy place to cancerous environment.
That's where so-called microproteins come in. Because they're smaller than regular proteins, they aren't as involved in the work the proteins do in the cell. But recent discoveries tell us that they may be more important to the cell's function than we previously thought.
So even though we think that maybe most of the small proteins that are made are spurious and not necessarily dedicated for a specific function, there are situations like in a cancer cell where by resorting to these kind of diverse set of proteins which are not part of the standard repertoire that a cell uses, cancer cells can try and find functional microproteins that help them to survive and to thrive in an adverse environment of a typical tumor. In my lab, we are interested in understanding how microproteins work. We are doing a kind of detective work in first figuring out which of the many thousands of candidate microproteins could be functional. And then we actually use methods to test function in a large scale in thousands of candidates at the same time, so-called screening.
Once they've narrowed it down to a handful of candidates they think might be involved when cancer cells fight to survive, they start to investigate them further.
For the screen, we use cancer cells that we transfect with our libraries, and each cell will get a different microprotein added or taken out. And after a while, after a treatment with chemotherapy, we look at which cells have survived and we read out the sequence of the microproteins that we've been targeting using next-generation sequencing.
The team removes one type of microprotein at a time with a gene scissor and then uses a variety of methods, including mass spectrometry, to analyze how the cell functions or dysfunctions without it. By mapping out how the different kinds of microproteins affect the cell, the research community will gain new knowledge that can help in the battle against cancer.
What I'm excited about in microprotein research is that here we have an opportunity to, first of all, discover basic biology that we didn't know about 10, 20 years ago. And at the same time, we can use that knowledge potential in the future to develop new therapies or new diagnostic tools. It took us 50 years to know that there's 20,000 normal proteins, so we can't be naive about how long it will take us to understand how many of the small proteins we have in the cell on top of those. But I think each discovery of a functional protein is, one more in an ever-growing list of potential disease-related proteins, potential drug candidates, or potential biomarkers.